Physics, and this small overview is an overview of Unit 5 from the AP Classroom on rotations. There are four main points to the rotations unit, and with many subpoints inside of there. So the first main point is torque and rotational static equilibrium. Second main point is rotational kinematics. Third one is rotational dynamics and energy, and the fourth one is angular momentum and its conservations. So I wanted to walk through these and what you need to know for the AP test. First of all, torque. Now, of course, we know that torque is the letter tau right here, and there is a few ways to calculate torque. But you will need to calculate the magnitude and direction of torque. And you need to know for the magnitude, torque equals your lever arm times the force, or cross product into the force. This will, if you do the cross product correctly, you will get your distance R, your moment arm R, times the force times the sine of the angle in between them. And that is going to give you your torque. The direction of that torque, you would need to apply the right-hand rule for the direction of what that torque is. If you are in a gravitational system, for example, if you are on some sort of object that is going to fall, you can take the center of mass, and that is going to provide a torque because of gravity. So you need to be able to use the gravitational forces as torques as well. And then what is the moment arm? And there's two ways to get the moment arm for torque. One is if you have a rotating system and the distance is r, and then you have a force acting on that at some angle, your moment arm is just that distance at which the force is acting. But you can also use a different r, which is the moment arm, to be able to figure out what the r is. And so you would have to imagine the force going back till it reaches a perpendicular. Probably the easiest is just to use the distance, use the force, and use the sine of the angle in between those. So that's torque. Related to torque is static equilibrium, and there's two conditions for static equilibrium. As we remember, there is the sum of the forces on an object, and you need the forces in the x and the forces in the y have to equal 0. Not combined, but separately. So you would have two equations for that. And then you also need to know that the sum of the torques is 0. So in a system that is in static equilibrium, which means it's not moving, and it's not rotating, and it's not about to, you could do that. So if you have several forces acting on a system in rotation, you can use the combination of these three formulas to be able to figure out the unknown for a static equilibrium question. So classic ones are, of course, you can have where you have a system with supports, and you maybe have some blocks on here, and somehow all of these things are in equilibrium, and you could do that. You may have a disk, and you have different forces acting on that disk, and you need to think about which direction all of those forces are acting, and they all have to add up to 0 to get that. So static equilibrium. In order to do much of these things, you have to be able to calculate your moment of inertia, which is your I. In general, the I is formula is mr squared. So whatever particle is out there rotating at a distance r, it has a rotational inertia of mr squared. But if you have several particles, then you have to sum up all of those things with this. There is the integral formula as well, which is our r squared dm. And we did a couple examples of that. If you were to not worry about something, that may be one thing that you could give up and not really focus on. So you need to explain the differences between the rotational inertia for different things. For example, a ring which has a width on it, something like this that rotates, its I is mr squared, whereas a cylinder that's solid, I'm going to try to draw this in 3 dimensions, is 1/2 mr squared. And now these look like the same. This one is just a hoop, and this one is a solid one. Why is the solid one less rotational inertia? So you need to explain the differences for those things. You need to calculate rotational inertia for various objects. The common ones that you need to know are rings, disks, spheres, and rods. You need to calculate for a system of objects. If you have more than one object kind of putting together to make a system, then you need to add the different I's together. And then it's going to be determine the I for just a mass, just some mass revolving around the point, which is mr squared, but you may have several of them. And then if it's off of the center of mass, we use the parallel axis theorem. So you need to know how to do all of these things. And I encourage you to make a formula list of all of these rotational inertias to be able to do that. And then the final thing, this is hard. This one is hard. If you need to skip it, but this is where you'd have to use calculus to be able to find the moment of inertia for a thin rod that has the same density. We did that example in class. For something that doesn't have the same density, and maybe the density changes, for a cylinder, those are ones that would be common on the AP exam. So calculating moment of inertia. Next is rotational kinematics. So this is motion. We have now our three parameters or motion things. We have theta, we have omega, and we have alpha. Okay, this is position and rotational position. Omega is rotational speed, and alpha is rotational acceleration. So you first of all need to be able to translate between those things. For example, omega is rotational speed, velocity is translational speed. So you need to be able to do all those translations between those different quantities. There's a set of kinematic equations for rotations that you would have the thetas, the omegas, and the alphas instead of the x, v, and a's. You have to be able to calculate using those kinematic equations, just like if it was one-dimensional motion, for example. You need to be able to determine the corresponding values. So we know that V equals omega R, and then A equals omega alpha R, and X equals the theta times R. And so you would need to be able to go between the two speeds. Calculate the linear speed. So this is V, and acceleration, which is A, at some point on a spinning object. So if you had a disk, for example, spinning, and we wanted to look at a little point right here and it's spinning around, you should be able to get what is the speed and acceleration of that point based on its omega and alpha. And then centripetal acceleration. Know how to use that. You should know both in terms of V and omega. And I was going to do force. Centripetal acceleration is V squared over R, or that's in terms of V, and in terms of omega, it's omega squared times R. So 2 ways of getting centripetal acceleration. All right, rotational kinematics. I think this is the easiest of the stuff on rotations. Rotational dynamics is applying Newton's second law to torque. So the sum of the torques not the sum of the forces, equals your I times alpha. So applying, this is Newton's second law for torques. So you need to be able to calculate unknowns based on using so if you needed to find the torque of something, maybe you need to find the moment of inertia, maybe you need to find alpha. That is a central concept that you need to use in rotational things. So calculate the alpha, angular acceleration is the alpha. Calculate the alpha using I torque. You can see this stuff up here. Center of mass, or maybe a point of rotation. So you have to be able to decipher all of that stuff. And these are common examples. So you could be rolling down an incline, rolling without slipping, for example. You could have a pulley system that is rotating. You could have some pendulums. A pendulum is a rotating object like this, and it could have an alpha based on the torque of gravity that is pulling it. Rotating bars. So if you have just a bar that's rotating like a baseball bat type thing. An Atwood's machine, there's two Atwood's machines. There's the one where you have this is regular Atwood's machine, where you have two masses like this and they flip and they start to rotate. A modified Atwood's machine is where one of the masses is on a table. That's the modified Atwood's machine. So you got the Atwood's machine. Pulleys that have rotational inertia, strings wrapped around discs, all of those things are examples of things that could be rotational dynamics questions. And then you would have to derive expressions without numbers for all of those things. So rotational dynamics, and then rotational energy. So you should be able to calculate your rotational energy. We know that the kinetic energy for rotations, very similar to the kinetic energy for translation, is 1/2 I omega squared is your kinetic energy. Instead of 1/2 mv squared, it's 1/2 I omega squared. So calculate the total rotational inertia with translation and rotations. So you would have to add your 1/2 mv squared on here. And then usually the v and the omega are related to each other, and so you can convert into those. So principles of conservation, if you have something that's rotating that's up high, and then it's going to start to, it's going to rotate and spin so that it falls down, and as it's falling down, it's rotating. You should be able to do that. You could use an incline for this. Find the energy to start and the energy to end. You could have an Atwood's machine where you have two masses on each side. You could have a pendulum, massive pulleys. All of these things are examples of using rotational inertia to use and calculate conservation of principles. All right, and the final thing that you need to know for this rotation section is angular momentum, and we just covered that. Angular momentum is given this L term, and there's two ways to calculate it. I'm going to rewrite this because it should be an omega, not a W. Is I omega, or you could have it as your linear momentum times R, which is mvr times the sine of the angle between the rotational arm and the momentum. So there you go. Calculate the angular impulse. Angular impulse is your change in L. So there is two ways to calculate this, but in terms of calculus and in terms of if you have a constant torque. But change in momentum is force times time. So change in angular momentum is your torque times time, like this. Or if you were to do this in calculus terms, it's your torque times dt. All right, and that gives you an impulse, and that changes your momentum, your angular momentum. So I'm using the right-hand rule, figure out what the right-hand rule, which direction angular momentum is. And then conservation of angular momentum is a very common thing. And usually you would use I omega equals I omega to use conservation. Whatever the your I may change in a situation, and you can calculate that. So calculate changes in angular velocity. So that's your omega when I changes. So examples, you could change the mass. Maybe you add mass or take away mass. You can change the radius. Maybe you bring in your arms or you put out your arms. You can add a disc. This is a common one where you have a rotating turntable and then you add a disc on top of that. And that's rotating, and you add another one on there. So you get two rotating discs to that. Collisions, if you had a rod like this and you had a mass coming and it collides with it, and then afterwards these things are going to start to move and rotate because this thing is globbed onto it. So it's going to rotate and it's going to move. That's a complicated system, but that is a angular momentum question that you can do, the conservation of angular momentum. It's very powerful if you use it right. And that's it.